Let's talk about reactions now, which is the learning objective for today. Let's see how far we'll get with this. And I may need to download this. So where we are right now, you must know what it means by benzylic carbon.
Yeah.
Benzylic carbons do react, and for them to react they must have a benzylic hydrogen.
Okay.
So that is the most important rule there, and you'll see the reaction happening for radical reactions and oxidation reactions like this, and that is where we are. So you're looking at benzylic carbon right there.
Okay.
That's benzylic carbon, and if it has a benzylic hydrogen like this and like this, if you have benzylic hydrogens, expect those carbons to be oxidized.
Okay.
So the first thing you want to do is to find your benzylic carbon. A benzylic carbon is one that is attached directly to the benzene. That's benzylic, that's benzylic.
Okay.
Now, as long as you have it, with my pen, as long as you have it benzylic, then you can expect it to be oxidized. And oxidation reagents can be potassium permanganate. I believe we usually do OH minus. I'll see what reagents you're given.
Okay.
Or even Jones. Remember Jones?
Yeah.
The H2Cr2O7. These two can oxidize your benzylic carbon to carboxylic acid for sure.
Okay.
Don't worry about the other carbons that fell off. Just maintain your benzylic carbon and make it a carboxylic acid.
Okay.
Now, the other summary, remember what I told you, you must have a benzylic hydrogen for this to happen.
Okay.
If I include a chicken foot here, he survives.
Okay.
So let me put that rule here. So for me in my lab I like using NBS and heat because I don't have the laser lamp. The laser lamp would have been better, but they're expensive. So again, you will see the bromines going onto the benzylic carbon. I just added a chicken foot there so that you can see the rule.
Okay.
No benzylic hydrogen, no reaction. It's coming in your test.
Okay.
No, I always tell you, then you see it.
No, I always do.
Yeah.
And then I'm like, oh.
Yeah, it's coming. This one is coming. There are those that I know that are common, those that I know are not common.
Oh my god, on my test, there was a question about, I don't even know what it was, but he didn't teach it. Like, I know for a fact he did not teach this. And you had told me that the night before, and I got it right. I was like, I don't know if this is correct, but I know most, like, said it.
Yeah.
But I don't know if it was referring to the question that I was being asked, and I got it right. So,
Yay.
but I know for a fact my teacher did not teach that. And I don't remember what it was, but it had to do with MBS.
Oh, okay. Okay.
Like, sparks.
Great. Yeah, if I see something that is not taught but I know it's common, I'll still let you know. and put FYI because you don't want to risk it.
No.
Just in case it's in the book, your teacher will be like, but it's in the textbook. Just
Oh,
because
yeah,
I didn't teach it, why did you not read it? And you're like, why are you my teacher?
I always read the textbook. I kind of just like for peace of mind.
Yeah, just to make sure that everything is good. So what I've written here is a summary of what you see here.
Okay.
Yeah, so the first thing you want to do is identify. This is your thought process. What happened to my handwriting? I've been writing since morning. Identify benzylic carbons, and then does it have hydrogens? If so, react it or it reacts. That's just the basic process of this.
Okay.
So in here, this is my benzylic carbon. I show you need at least one hydrogen. Don't have to have plenty of hydrogens, just one.
Okay.
Because oxidation is loss of hydrogen. Oxidation is loss of hydrogen, oxidation is gain of oxygen. So if you don't have hydrogens to lose, how are you going to oxidize? Yeah.
Got it.
Don't worry about the rest of the junk of carbons. Those are usually lost as carboxylates, but again, you're not going to be tested the mechanism on this. So here, smiley face is going to work.
Okay.
And that very carbon is the one that's going to get a carboxylic acid. I hope you still remember your functional group.
Yeah.
You'll excuse my handwriting. I've not been writing as much, but I've been grading since morning. So my hand is like, can we go sleep, please? Not before we play some music. So now you will tell me case A why there's no reaction. Why is no reaction in A?
Because,
Mm-hmm.
well, there are benzylic hydrogens, right? 1, 2, 3. Yeah. There are, but Jones can't react with a tertiary hydrogen, correct?
No, you're just a wild goose thinking all over the place. You need to come back
But
in class.
it's more simple than that.
Yeah. Did you follow my rules, my steps, thought process?
No benzylic hydrogen?
Thank you.
Or,
Those are phenylic. These are phenylic carbons with phenylic hydrogens. Those are not benzylic.
okay.
Those are phenylic because that's a phenol ring.
Got it.
So no reaction reason, no benzylic carbon and hydrogens. After that, you will tell me why B there is no reaction.
It's not benzylic at all.
There's no phenol ring, no benzylic carbons, no benzylic hydrogens. The same thing.
And then the last one, it is benzylic, but there's no benzylic hydrogens on it. But there's benzylic carbon, but no.
Yeah. The chicken foot I showed you.
Yep.
You see, which is why I'm telling you, this chapter can be extremely easy if you know the rules. If you
Okay.
don't know the rules, you'll be like, wait, why? Why am I wrong? What? What happened? I'm right. No, you're not.
Okay.
Now you go to the next one. The reaction may be performed with potassium permanganate. Growing up, I think in the 90s, okay, being a teenager then in the 90s, tooth pain medicine was not much available.
Okay.
So my mom would take this, and they are crystals, they are purple crystals. She would take this and stick in my tooth whenever I have a toothache or whenever I have an infection in the mouth.
Got it.
Then tells me, don't swallow it, let it stay there. Then I should be fasting for a couple of hours, and
Okay.
the toothache disappears, the infection disappears, because these are very strong oxidation agents, so he kills bacteria by oxidizing them.
Okay.
But the problem is the pee, the poop will all be purple.
Oh my god.
Yeah, for a whole week. It's a very strong stain.
That's crazy.
So here I do have a benzylic carbon. Do I have hydrogens?
Yeah.
Yes, I do have them. So this should work. Keep it. And so that's gonna be oxidized. Now remember that there's no H3O plus, which is why if you check here, I did 2 steps.
Mhm.
The first step is gonna give you a carboxylate because it's basic.
Okay.
The second step will protonate the carboxylate.
Okay.
I'm surprised there's no OH minus, but I do know H2O and heat will still work.
Okay.
So the carboxylate just receives a proton by protonation to give you the carboxylic acid. Mechanism is avoided, is quite complex.
Okay.
Let's talk about NBS. Did you get any mechanism question in the test or no?
Not on the last exam, no, but he usually does do mechanisms.
Alright, so we'll review this NBS thing. I usually use 2 equivalents and do homolytic cleavage, meaning 1 electron
Okay.
breaks side. Homo means similar, same, and that's why we're called Homo sapiens. We walk upright, all of us. Okay, so you get a radical and a bromide, actually 2 of them. This step is the I step. We call this initiation.
Okay.
And that right there is your N-bromosuccinamide. Let me give you the name just in case. I've given you the structure. But the name is N-bromosuccinamide. So if you see the name, you just know it's NBS. NBS. Derived from succinic acid. Usually before I use it in the lab, I do recrystallization, maybe overnight, filter it and then use it. Because it gets stained with bromine.
Okay.
Anyway, then we're going to do the P step, which is propagation, which is where you're going to find your benzylic hydrogen and you're going to pull him out by homolytic cleavage. Mm. To give you a very stable benzylic radical. It's stabilized by resonance, after which you are able to do your final step, which is called termination. And would definitely get enantiomers out of this. Let me just show the regular thing without wedges. Which is what you're seeing here.
Do you think I'm gonna have to draw the mechanism for this one?
No, I don't think so, but I'm showing you because it's been something you've learned recently. Substitution and elimination proceed via carbocation and benzylic composition. We know it's because you're getting a. If this falls out, you're going to get a more stable carbocation. It's tertiary and benzylic, meaning it's resonance stabilized. And so we show the resonances. You're good with resonances. Yeah. Then the H2O attacks. This chapter is mechanistically heavy. The mechanisms that you need to really practice are coming.
Okay.
So you get water attacking there, then you do proton transfer. Just as typical SN1 from organic one. You get your product. Okay. Same thing here. Once the you're going to protonate this to make it a good living group, and that's gonna fall out to give you a carbocation, and then to get here an H2O molecule will remove that extra hydrogen from here. You get your product. That's E1, dehydration. So it's just showing you other reactions on benzylic carbon.
Okay.
Good thing the things you did before. Are you okay with that?
Yeah. I'm gonna have to practice a lot this weekend.
Yeah, I hope you can still see my screen.
Yes, I can. So you think I should just like continuously, like no matter what practice mechanisms?
Just do it. You just
Okay.
never know.
Okay.
And the good thing, if you practice mechanisms, you see a reagent. If you are not asked for the mechanism, it's an added advantage.
Yeah, okay.
Because you can find the product if you blank out using a mechanism. SN2 is simple. Still the same benzylic carbon. And then E2 is where you use a strong base to pull out that hydrogen.
Okay.
No carbocation formation. They forgot to put heat. Is it still snowing there?
I don't know, my windows are closed, but it was 80 degrees yesterday, and then we got like a literal blizzard for like an hour. It was snowing so hard.
Oh no.
I know, I like was taking an exam and I left, and I was like, what is going on? It was really nice this morning, and then I don't know what happened, but it's freezing out now.
I hope you have very cozy, woolly, warm jackets.
Well, I didn't wear a jacket today. I just wore this sweatshirt, and oh my god, I was so cold. It was so nice.
You pee on yourself.
Yeah, it was awful. At least I had an umbrella today, though.
Yeah.
It was like really snowing.
So these are summary of all things we just talked about. You can oxidize. You know the rule for oxidation? Find the benzylic carbon, make sure it has at least one hydrogen.
Okay.
And that's going to be substituted if you do NBS, heat or light. Or you can do the Jones or the stain, potassium permanganate.
Okay.
These two can give you the same product because he has a benzylic carbon, benzylic hydrogen. The same hydrogen can be replaced by bromine. And then we don't expect SN2 here. Do you know why?
Because it's tertiary.
Thank you.
Yeah.
But SN2 can work here because it's primary.
Okay.
However, because it's benzylic, even SN1 can work.
Okay.
Because the carbocation is benzylic, is resonance stabilized. So this is just a summary of everything. We don't need to emphasize much on it as long as you got the gist. There's bigger reactions to come.
Okay.
You have
Everything I ever one slide.
yeah. So now I told you that. Okay, let me ask you this way: why would benzene double bonds not do 1-2 additions?
Because it can do resonance.
Yeah, they are always running all over the place. It's like you trying to catch a mouse or a mouse in your apartment with your hands. Good luck. All furniture will go to the floor, but you'll still not catch him.
Yeah.
Until you use a trap with cheese. It doesn't take time.
Okay.
The neck will be trapped. So you need, if you want to reduce, if you're just doing a regular reduction, for example down here, this is what's gonna react. So this double bond is not aromatic. That's gonna be reduced. Look at the conditions. Easy, soft conditions.
Okay.
But here, if you want to reduce the one in the ring, those are all aromatic. You're gonna need harsh conditions.
Okay.
100, right now where you are, it's just under 1 atm. That's the room pressure. Under 1 atm. Imagine 100 atm. Pressurized. And then the temperature is 150 degrees. 50 degrees above the normal boiling temperature of water. And then you have to use a more reactive catalyst, metal catalyst, nickel, instead of platinum.
Okay.
So everything is just exaggerated for benzene to be reduced. But we do have another catalyst called Rini. Is it Rini or the red rhodium? One of those does not need this harsh pressure and temperature. But the catalyst itself is extremely expensive.
Got it.
Now you can also judge by the heat of reaction is 208, or this is 117.
Okay.
Yeah, and I've done this reaction multiple times similar. Only the external double bond gets reduced. The internal double bond stay.
The delta H. So is that saying like what exactly is that saying? Like it's more stable.
Okay, so it's very, you see how negative it is? That means that for this reaction to happen, you're gonna release a lot of heat energy. So that tells you the original molecule was very stable.
Okay.
Extremely stable, that it will not want to react.
Got it.
Yeah. However, if you are thinking the other way around, someone would say there's high energy stored in the benzene than cyclohexane, but that's a different way of looking at it.
Okay.
Just know that benzene will not want to be reduced. That's all we are saying.
Okay.
Okay, so batch reduction.
Oh my god, again.
Yeah, but it's a different thing. It's not the cis trans.
Okay.
Usually alkynes by batch reduction. Let me give you a review. So if you have this and you give in batch, you would get trans.
Okay.
But we say that if you give it Lindlas,
That's the cysteine.
yeah, that will give you the boat. But here we are talking about the benzene ring. And for the benzene ring, you just want to reduce and have the double bonds across. Again, the mechanism can be shown, but it's not tested. This mechanism is usually not tested. It's crazy. Bunch of half arrows. It's not difficult to memorize, but anyway, I'll not explain the mechanism. I'll just tell you what's happening here.
Okay.
So eventually, huh?
Sorry. So just know they have to be across from each other always.
Yeah,
Invert.
the variable is gonna be whether you have an electron donating group or electron withdrawing group, and I'm going to give you the shortcut for your flashcard. So if you have if you have an electron donating group, make sure that at least one of those two double bonds shares a carbon with the EDG.
Okay.
Okay, on the other hand, if you have an electron withdrawing group, those double bonds should shy away from the EDG, from the EWG. So if you memorize that rule, you should be fine. Moving forward, there's a table that will tell you who is electron withdrawing, who's electron donating, but from Diels Alder, you know who donates, who withdraws. So you get an isolated alkene.
Okay.
So if you look,
Sorry. So I guess the ones with the electron donating groups, the pi bonds are basically closer to each other in comparison to the electron withdrawing groups. Is that like a good way to put it? I guess they're both one carbon.
no, they're one carbon away. The main thing is to know that you have to share a carbon with the EDG here.
Okay.
But the other one, you don't want to share a carbon with the double bonds. That's the main thing. And you can see the example down here. By the way, the reagent is always sodium, methanol, and liquid ammonia. Carbonyl containing compounds are moderately deactivating, moderately electron withdrawing. So I show the arrow pointing towards outside the ring. And that means that my double bonds must shy away.
Got it. Okay.
This is said to be reduced because he received a hydrogen that he did not have. Reduction is addition of hydrogen.
Okay.
This one will be minor or not made. Because the double bond shares the same carbon as the electron withdrawing group.
Okay. Why does the one on the left say not like why is that one not reduced? Like, or is it because it's the electron donating group on it?
Because we are
Like,
assuming that this is we are assuming that this is an electron donating group.
okay.
You're assuming that you have an alkyl group like a methyl group. Those are electron donating groups. Alkyl groups are electron donating through bond. They are weakly electron donating.
Okay.
And in that case, this will be minor or not formed.
Okay.
So assume on the left is EDG, on the right is electron drawing.
Okay.
Like I said, I'm not talking about the mechanism. That one is not very important
Yeah, if
to
he
us.
tests on that, I will be shocked. It's a long one.
I wonder why he would do that. But anyway,
I hope he does.
if we have extra time, we can come back to it.
Okay.
Predict the product to that. I could go on and on and on and on, but anyway, those three are enough for your dose prescription.
So NO2 is a withdrawing group.
Okay, so are you referring to this?
Yeah.
Yeah, that's electron drawing group.
So they're gonna be as far away from that as it can be.
Correct. Draw your product before I draw mine.
Okay, I did it.
Okay, so we need one to share with the EDG. That's an EDG, there's a lone pair. Okay, so we know this is electron donating. So if I do this already for the electron donating, that satisfies the NO2 anyway.
Okay.
Okay, then we'll do the next one. I hope you got what I got.
Yeah, I did.
Okay, let's see. Try the next one.
Um, OH is a donating group, so they're gonna share one carbon with it. Or yeah.
Yeah, but the diagonals have to be opposite. This one is also electron donating. So
Okay.
him too gets to share a double bond on the other side.
Okay.
Hmm.
Are they both electron withdrawing?
Yeah.
Okay. So they're gonna like be far away from each other, if that makes sense.
It should be like that.
Yeah.
Then you got the concept if you got them right. Just the rules apply. Rules apply. Rules apply. Mm-hmm. Now.
Is there more Adam? Oh my god. I don't mind IR. It's like I don't really mind any of it. It's just like I know it's gonna haunt me for the rest of my life now.
uh, well, I already taught you.
Yeah. It's like my lab. It's one experiment. It's every lab I did in Orgo 1.
Yeah.
It's crazy. Like, I don't know how one person should know that, like, that much information.
You're a super lady. We expect. We have a lot of faith in you, you know. So don't disappoint us. So sp2chs, they should be around 3010 wave number. But I remember I told you about these TDs right here. Yeah. Those are called overtones. And also we usually have bend modes, not just these, including these.
Okay.
Those usually denote aromatic.
Okay, at the very end.
Mm-hmm. Remember how you were told that not to worry about the fingerprint region?
Now I have to concern myself with
Nah, they lied. They lied. See, the carbon C is right there. But because of resonances and variations in bond length, you'll have multiple stretches, but they're the same thing.
Okay.
Yeah. And that's it they're telling you here, nothing much.
So I'm assuming on like every exam from now on I'm gonna have an IR.
Yeah, you don't want to assume CNMA.
Okay.
But let me see how you're gonna explain it to me. So I need the multiplicity stuff.
What happened?
Multiplicity, M value.
Oh. Oh my gosh.
So what is M value for A?
N minus 1, is that the rule?
No, N plus 1. You rusted already.
I know. I know that the one that has the 5 on it is a singlet. So neighboring.
Yeah, but that is that's an assumed singlet, but it should be not. It should be a multiplet.
Wait, what am I supposed to be like? Oh, okay.
We look for the N. The neighboring hydrogens for A is 2.
That's 2 plus 1, so it's 3.
Yeah, so it's triplet. So that's why this is an A. It's a triplet.
Oh, that one down there. So the other one's a quartet because there's 3 next to it, and that's the CH3 group plus 1 is
Quartet.
or the triplet.
Yeah, and then it's benzylic. That's why it shows up between 2 and 3, just like alpha carbons. And then these are phenylic or aromatic. They show up at, these ones will show up at 7-ish.
I wish I'd never had break. It like ruined me.
You went and erased everything you've learned.
Yeah, like we have lab today for orgo. Oh my god. I have never had a worse lab in my life. It's like I've never walked in an orgo lab before. It was awful.
You did, you were lost. You didn't know what the procedures were saying.
It's just like nothing was working. Like It was awful. Like my
Was it
reaction
Fischer
was just
esterification?
what happened?
Was it Fischer esterification?
No, it was nucleophilic aromatic substitution.
That it should be easiest.
It was me. Like I was just having a hard time. Like all of us in the lab were just like not having a good time, and our TA was in a bad mood, so it just got worse. And my professor had no clue what was going on either, so it was rough.
Yeah, whenever I do, it's been a while since I taught the second organic lab, but whenever I do it, it usually just works. We do EAS with toluene and bromine, liquid bromine, and they test using a blue litmus paper. It just shows like it's bam bam. Even this oxidation with Jones, the color changes to green. Bam bam.
Oh, ours wasn't like that. We did like my part. I had to isolate 2,4-dinitrophenol. I had to do that.
2,4-dinitrophenol. So you started with the phenol and added nitric acid.
Yeah.
The problem with that is just a very, very messy reaction that I don't like doing.
Yeah, my reaction was to be light yellow and it was black. So I was like, I don't really know what's
Uh,
going on. So.
You broke the molecular part.
Yeah, and I did everything right. Like I know for a fact I did, but whatever.
Anyway, so this is talking about the integration stuff. We don't need to go there, but I want to give you a clue. Anytime you have a para substitution, so maybe you have a group here. Oh, let me even be clearer. So suppose one side is an OH and the other side is a chicken foot.
Okay.
These two hydrogens are not the same as these two hydrogens. And so both of them will be their own doublets, different doublets.
Yeah. Okay.
Now the one,
That's just because there's no symmetry in the molecule. So even, no matter which way
symmetry
you split
is there this way, but it's
Okay.
not there this way.
Yeah. Okay. See, that's why they're their own things.
Yeah, and I expect if I call this HA, HA will be here. They're shielded next to electron donating group,
Okay.
and then these ones will be the HB.
Okay. Oh, I see. Okay.
So what this is telling you is that if you're ever given an NMR and around 7 you have doublets, two doublets, just know that you have a phenol ring that is para substituted.
Okay.
Then you can go from there.
Okay. I can do that.
Para substitution in proton NMR is shown by this.
Okay.
Okay.
But is it so like the one on the left is so that's still para substituted, but you're not gonna get two doublets
because of the substituents being
Same.
symmetrical.
Yeah.
Okay.
Okay, so if I see two doublets at 7, I'm gonna get a para substituted phenol.
If
with
you see
two
one signal,
Uh-huh.
there's no splitting because they are similar. If you see one signal, 4 hydrogens, you know it's para substitution with similar group up and below. So something like this.
Okay.
All these hydrogens are the same. They should show up there as a singlet.
Okay. Got it. So then the other one with the two doublets, they're obviously different.
Correct.
So I'm gonna get para substituted with different constituents on each.
Correct.
Okay.
Yeah, they're just explaining that it's an isotropy that is causing the peak signal going to 7, the shielded.
Okay.
Because I think the protons are aligned to the magnetic field. Okay, So that's all we've been saying here.
Okay.
So if you have, come on, why are you saying you have 3 signals? There's no 3 signals here. This is carbon NMR. I thought it was proton. It's carbon. Okay, if it's carbon, then I know that this and these are the same.
Okay.
And then these are the same. We expect 2 signals.
Okay.
Because our substituents are same. Assuming you'll not be given the depth, 95 and 135. And then here, same. No. These 2 are same. The middle are the same. And the top ones should be the same. Because of symmetry here.
Okay.
Internal planar symmetry. Here, these are different. So you expect 4 different carbon peaks.
And there, you expect the 4 signals because on like the bottom one, is it because there's no pi bond on that like bottom flat bond? Does that make sense?
Where here?
On the 4 signal one.
You're saying there's no pi bond?
Like, hold on.
There's a pi bond.
It's trying to figure out why it's 4 signals.
Okay, it's 4 signals because the carbon on X is different on the carbon on Y, you agree?
Yeah.
And now, you can split the molecule into equal half and
I
cross.
see.
So the blue and the blue, you count it as 2. And then these green and green, you count it as 3.
Okay.
And then of course the other one is 4.
Okay.
This one, all of them are different.
Yeah, there's no symmetry no matter which way you cut it.
Same thing, all different. That makes sense because if you're cutting this way, then this is 2, this is 3, 1, 4. 2, 2, 1, 4, 3, 3. Yeah, 4. So just different ways of cutting it and seeing the similar signals.
Okay.
Yeah, you're not running away from NMR. Nope. Nope.
Yeah, you need to get to remembering this
Yeah.
weekend.
That would be a lie. Let me see the recitation. Let's see if you can see what the answer is. The answer for this one. I know there's a second part to this chapter that you've not sent the notes.
Yeah, he hasn't posted it yet. I just looked.
That's the one that has a lot of reactions.
Oh, so fun.
That's fun, right? As long as you
Yeah.
can get your smoothie from Smoothie King. I don't know if you have Smoothie King on those areas.
I think so.
You don't have Smoothie King?
No.
You're missing a lot on good things.
You know what's good? They only have it in Florida. Tropical smoothie. That place is really good.
Tropical smoothie. I've not tried that.
It's really good.
I make my own smoothies, and my wife
Yeah.
likes to experiment with different smoothies because she uses that as her dinner while at work. She's a nurse, night nurse.
Oh, she has no time.
Yeah, she has no time. So once she eats at 5 when she's leaving. She carries her big cup of smoothie, and that will take her to the morning. So
Oh my god.
I'll be there waiting. Um,
That's
I'll be
great.
benefiting from that. Once she leaves, I'm like, what did this woman make? I steal some. Okay, so this is naming for 17A.
Yeah.
It says 2,4-dibromo chloroanisole. Now you told me that you're supposed to take time and memorize the bunch of ring structures.
Yes.
Anisole will have OCH3. Don't confuse it with the one with NH2. Do you know what the name is for the one with NH2?
No, I haven't memorized that.
That's an aniline.
Okay.
This is anisole with OCH3. And then we have something, so this will be number 1. Number 2, you'll have a bromine. 3, 4, 5, and 6. You're going to put there another bromine. And then number 4, you have a chlorine.
Okay.
Yeah. So it's very easy to do.
Yeah, I just have to memorize the structures.
Yeah, memorizing the parent structure is the catch here.
I can do that.
Uh-huh.
Not too bad.
For B, nitrophenol. The main parent ring is a phenol. A phenyl ring with an alcohol, phenol. Phenol.
Like I would have not done that.
Yeah.
But like looking at it at first, you know.
Yeah. Meta means position 3.
Okay.
Auto is position 2. Para is position 4. You must have seen that in the lab. So let me see if I can just.
You said ortho position 2.
2, 6 is auto.
Okay.
3, 5 is meta. So this is what I do. I draw the ring and I say this is my group. This is my reference group. So auto is position 2 or 6.
Okay.
Meta is position 3 or 5.
Okay.
Para is always position 4. Opposite.
Okay.
Next door is auto, 1 carbon over is meta. Yeah, that's how I do that to remind myself.
Easier.
Yeah, very easy. So now our phenol will have an OH, and on position 3, that's gonna be the meta.
Okay. So the phenol is like the main one, and we know that that has to go at that certain position.
Yeah, you start with the parent group.
And then doesn't like when you add the alcohol to that, doesn't it always go to position 1, so then you count to 3 to get to position 3 for the meta?
Yes,
That's correct.
just
Okay.
like when we added the OCH3, that counts as 1 because it's what called the shorts to name the parent ring.
Okay.
Is A aromatic? Let's finish with 1711. Is A aromatic?
I can use the rules for that, right?
Yeah, the 4 rules.
Like the okay, yeah. 1 second. Okay, it is cyclic.
Conjugated.
Does that count as conjugated even though there's only one
Yeah,
ion?
because you can move it.
Okay. Conjugated, planar, yes, flat. And then the n plus 2 rule is what we're trying to do. So there's 1, 2, 3, and then 4 counts as the lone pair, right?
Mm-hmm.
So,
Hold on, math. I'm not too good at that
It's
one.
divisible by 4. What did I tell you when anything divides
so
by?
it's not aromatic.
So what it is? What
Um,
is it? It's anti.
No. Oh. Non-aromatic is when it's...
It
What is
fails
that
1,
again?
2, or 3.
Okay.
This fails 4n plus 2, passes 4n.
Okay.
But it's gonna be the opposite for this. This has 2 pi electrons.
For cation. Okay.
Yeah, 4n plus 2 is 2. 4n equals to 2 minus 2 equals to 0. 4n equals to 0, n equals to 0. Which qualifies, it's not a fraction.
Wait, 4n plus 2. Where are you getting 2 from? Wait, I'm sorry.
2
Yeah,
pi electrons.
Oh, I see.
4n plus 2
Okay.
equals to number of pi electrons. Then you solve for n. I subtracted 2 on both sides to get 0. So 4n equals to 0, n is 0.
Okay. Got it.
N can be 0. 0 is not a fraction.
Got it.
What? I think that's my email. And then this one is 1 check, 2 check, 3 check, 4. 4
So
pi
it's
electrons.
plus 2, 4 pi electrons, so no.
You don't use 4n plus 2, you're gonna use 4n.
Why don't you use plus 2?
Because it will give you a fraction. 4n plus 2, remember again, you have a number of pi electrons are divisible by 4. That's the shortcut to note it's n-type. Especially if you're checking off 1, 2, 3. So 4n plus 2 equals to 4 pi electrons. Let's test. 4n equals to 4 minus 2. 4n equals to 2. N equals to 2 over 4 is 1 over 2. It fails, which is why I did not want to test it anyway. Since I know 4 pi electrons is divisible by 4.
So if I know it's divisible by 4, I can not do the plus 2 and just do 4n equals the number of pi bonds.
But no, you are testing for anti.
Okay, so that's proving that this is anti and not aromatic?
Yes, if and only if rule 1, 2, and 3 were correct.
Okay.
This is 10 pi electrons, I hope you know that.
So,
Count your small fingers.
is it aromatic?
It's not divisible by 4. It's not. There's no hydrogens close together to crowd. Rule 1 check, rule 2 check, rule 3 checks. Everything is sp2 including the one with the lone pair. You don't count lone pair towards hybridization because it's doing resonance.
Mm-hmm.
So 4n plus 2 equals to 10 pi electrons. 4n equals to 10 minus 2. 4n equals to 8. And n equals to whole number. That's gonna be aromatic.
Got it, okay.
We'll continue from there next time.
Perfect. And hopefully you post those slides. So you're
Yeah.
gonna need them.
Then we'll go over them ahead of time.
Yeah.
Oh, look what we have in 17.5.
Some lovely birch.
Easy peasy.
Yeah. Okay, I'll work on these, and if I have any questions, I'll let you know on Saturday. Does that work?
Yes.